Hello, in this video we're going to take a look at section 3.1 on measures of center. So a measure of center is a value that represents the center or middle of a set of data. The question then is, what do we mean by the center or the middle? So most people, their go-to measurement for this is the average, which we are going to try our best to start calling the mean. But that is not the only way of measuring a center of a set of data. And which measurement you use depends on what kind of information you're interested in, and also what is more representative of the data that you're working with. So, and also maybe based on context, right? So in certain circumstances, one measure of center might be more objective and a better representation of what's going on than another measure of center. So the mean or the average isn't always the best way of measuring the center. It's the gold standard, if you will. It's the measure of center that is used most frequently and that is best understood. But there are definitely some situations where the mean, the average, is not the best thing to use. And we'll talk about one of those sometime during this video. So there are going to be 4 measures of center that we consider in this section, 2 of which we will continue to see throughout the rest of the course, and the other 2 you probably really won't come across again, at least the way I teach the course. The funny thing about all of these measures of center is that they all begin with the letter M. So there is mean, median, mode, and mid-range. And we will talk about what those are and how to calculate them and do some examples with those concepts. So let's go ahead and take a look. The mean is the number obtained by adding up all the data values in a set and then dividing by the total number of data values in. So remember, we've seen that here and there so far in this course, that the letter N is used to represent the total number of data values in the set. From starting now, we're going to make heavy use of that. So I've sort of introduced it previously, used it here or there, but from this point on, that's going to become a pretty standard thing for us to use. So you'll need to make sure you recognize whenever you see N equals blank, that's telling you the total number of data values. The mean is more casually called the average. For whatever reason, it's frowned upon to call it the average. I don't know if it's just imprecise language or what, but mean is what we want to start calling it from this point on. All right, so I'm going to show you a formula for the mean. Now, the way we find it is to add up all the data values in our data set and then divide by the total number of data values. So it's more easily described than it is formulaized. So in math, we like to have formulas for things. So how would you make a formula out of that description? Add up all the data values and then divide by the total number. I mean, you could use words, right? You could say, the mean equals the total of the data values divided by and that's even a little bit imprecise, right? The total of the data values. Does that mean the total number of data values, or does it mean, so maybe I should be a little more careful about that and not say total of the data values, because that really could be taken to mean a couple different things. So we would add up all data values. Let's word it like that. Oh, that's a horrible L. Sorry about that. It's still bad. And then divide by the total number of data values, which we could just call N, but I'm gonna make a point here that using words, it's a bit clunky and not really what you think of when you think of a mathematical formula. So what always happens in mathematics is anytime a certain concept or phrase would get used repeatedly for some kind of situation, in math, we like to invent symbols. I was about to say formulas, but invent symbols to represent those concepts. And so that's going to be the case here. Adding up all of the data values is a really common thing to do, especially in statistics. And we don't want to have to write it out in words every time. Add up all the data values, add up all the data values. So we have some symbols to represent that. So remember in mathematical language, adding up something, the technical word for that is sum. And in Greek, the letter S in Greek is the sigma symbol. And there's two versions. There's a capital sigma and a lowercase sigma. And we actually use both in statistics. So we have to make sure we keep them straight. For a sum, we use a capital sigma. And so it looks like this. It kind of looks like an E. And that's maybe not the best drawing of it. But that is a sigma symbol. And whenever you see sigma, that means you want to be adding up whatever follows. And so if we want to say, let's add up all our data values, instead of saying the word add up, we could use this in its place. And the data values are represented as a variable x. And so we let x represent a random data value in our data set. And if we want to add up all the data values in our data set, a symbolic way of making that statement is to write it like this. Sigma x means add up all the data values. And then divide by the total number, which we call n. And so that would be how we formalize it. I don't know, how we symbolize it in mathematics. So we don't have to keep writing out those words. We use these symbols instead. And so that's what you're going to see on this screen here. Right. So I was going to go to that screen, but I didn't want you to be scared right away because it's pretty, it's strange looking, right? And so this just means add up all the data values and then divide by the total number. And this is a great way of introducing this notation because we're going to see it again with some other concepts, but at least with the average, you already understand how you're supposed to do that anyways. You add up all the data values, divide by the total number, and this is what that looks like when you represent that procedure using symbols, mathematical symbols. This is the symbol that we use to represent the mean. And specifically, you'll see there's another symbol down here. This is the symbol we use to represent the mean when the data values we're using is a sample. I don't know if that grammatically made sense there, but if we're finding the mean from a sample, this is the symbol that we want to use to indicate that. Right, so X bar is how you read this, and that indicates the mean of a sample that you're working with. Contrast that with this symbol, which is also a mean. This is a Greek letter, and this Greek letter is the Greek letter mu. And so it's like an M. It's the Greek letter M for mean, right? But this symbol only is used to refer to the population mean. Now, this is a really important distinction that a lot of students, it just seems to go over their heads. And we talked about it in chapter 1. I still have not recorded the chapter 1 videos yet. I probably will go back and do that after I do chapter 3. I'm not really a statistician. I'm more about math. Now statistics is math, but let me put it like my degree was in pure mathematics. I didn't do applied mathematics and I didn't do statistics really. Now that being said, I did take a couple of statistics classes and, I've taught this class a few times and I've gotten a lot better at understanding the material and explaining it. First couple of years were probably kind of bad, but I'm pretty good now. I feel like I can't even remember the point I was trying to make. Okay. So, what was I even trying to say? I don't remember. Oh yeah. What goes over students' heads, is that, and we talked about it in chapter 1. I don't know why I'm going in circles now. I might need to just cut this out of my video when I edit. I need to edit it out. So there's a major difference between sample and population. We normally will not get to know the population mean. It's very rare that information is ever available to you, but we have a symbol to represent it because it's an important concept. And whenever we're taking a sample, it's in the hopes of better understanding the population. So remember the difference there between sample and population, right? We're studying a population, an entire group of people. The issue there is that it's very difficult to collect data from every single person in a population. Even if you think of just like a single city, like Dodge City, right? There's 30,000 plus people here. If we wanted to get data from all people in Dodge City, that would be a huge undertaking and really difficult and maybe even impossible to track every single person down to collect that data. And impractical, it would take a lot of resources. It would be expensive and maybe, so there's a balance that we're trying to find. We want good data that represents the population we're trying to study, but we can't spend millions and millions and millions of dollars or billions of dollars to collect that data necessarily. Or we don't have the time to go out and track every single person down. So instead of trying to get data from everybody in the population, we instead pick a sample of that population. We get a subset of that population, collect data from the subset, and then just hope that that subset was representative enough of the population. So most of the time, the scenario you're going to find yourself in is that you're studying a population, but you can't have all the data from the population. So instead, you get data from a sample that comes from that population. And then you study that sample, and then you hope that the information you get from that sample is representative of the population and is close to the population value. So for example, for the mean, we hope our sample means are representative of the population mean. So we hope that X bar, the mean we get from our samples, is equal to the population mean. It won't always be. There is variation, and every sample that we get, it's going to vary a little bit and may not always equal the population mean. But we hope that it's a good approximation. So I use the squiggle line here to say we hope the sample mean is approximately equal to the population mean. We hope it's close to it. And sometimes it'll be dead on. Other times it actually might be far away, because you can get unusual samples that really aren't very representative of the population, not because you did anything wrong. It's just natural fluctuations in the kind of samples that you might get. And so we are going to most of the time be finding X bar, and that's how we should normally label our means, unless the problem specifically says otherwise, that you're dealing with a population. You should just assume the data you have is from a sample, and when you're finding the mean of that sample, it should be represented with X bar. And that we hope X bar is somewhere in the neighborhood of mu. Okay, so that's why we have a symbol for that, because it's our goal. Right? We're hoping our X bars are telling us something about our mu's. All right. So sorry about that tangent, but it's a really important thing. And because what has happened, and it's really been almost heartbreaking to me, is, we'll take our first test and I might have a question on there about explain the difference between sample and population. And it's a very critical, core, fundamental concept of statistics. And I will get sometimes classes that cannot answer that question. And it almost makes me want to cry, because that is necessary to understand what we're even doing here, right? So the population is the entire group that you're studying. A sample is just a small collection, a small subset, I can't think of another way to say it, of the bigger group. And we study that smaller subset, get information out of it, and then hope that if we chose our sample well, the conclusions we're drawing from our sample hopefully apply to the bigger population. And the reason we can't do the entire, so sometimes students will say, well, it's, this data is not good because it's from a sample. That's the only way we really can draw conclusions about populations, is from samples. It's really most of the time impossible to collect data from an entire population. So again, this is another case, and maybe I will have mentioned this in the chapter 1 videos when I finally record those, but let's say you're studying a population like the United States, and you get a sample of 40,000 for that study. That might seem like a small number relative to the size of the population of the United States, but 40,000 is a humongous sample. And if it's chosen well, if the sample is done randomly, it should be quite representative of the entire US population. 40,000 is a great sample size. You normally get, like, if you look at study, like, surveys, like these political polls and stuff like that, that these different organizations do, they're usually in the 2,000 to 3,000 range for sample size. And that's pretty reliable to within, 2.5%, 3% margin of error. So 40,000 is incredible as a sample size. And yet on the test, when students are asked what's wrong with this situation, they see the sample size of 40,000 and they think that's the problem. That's too small. That is humongous. That is not the problem. And usually if there's a problem, it is in how the sample is collected, not the size of the sample, but how you collect that sample. That tends to be the issue. If you're not collecting it randomly, then you don't get a representative sample. And it doesn't matter how big the sample is. 40,000 is huge, but if I choose that sample poorly, then it's not representative of the population. And any calculations, any conclusions I draw from that sample will mean nothing if it doesn't represent the population that we're trying to study. Okay, so I just want to reemphasize that point. Hopefully I drilled that in chapter 1, but I want to reemphasize it now. We're getting to the end of chapter 3. We'll be getting to our first test, and that's a really, really, really critical concept for statistics to even make sense. If you don't understand the difference between a sample and a population, then this whole course just won't make sense to you. It's really important for you to understand that. All right, so let's take a look at the data that we've been using throughout chapter 2. We're going to try to continue to use it for chapter 3. The difficulty I'm a little bit worried about is I actually don't have a calculator with me. I've been sheltering at home. I haven't been to my office in months. I think I have a calculator in my office, but I don't have one at home. And this is a large data set. Even if I did have a calculator, it's 107 data values. That's going to be a lot of typing into my calculator. Even if I have a shortcut, I still got to get the numbers in my calculator one way or the other. And so I was kind of thinking maybe I can't use this data set for the lecture videos because I don't want you guys to sit here and watch me type in 107 numbers to get the mean, because what do I have to do? I have to add these up, right? I have to take 100 plus 100 plus 94 plus 93 plus another 93, all the way down to the last data value, which is 80. So I'm going from here to here, skipping a lot of the detail, but I have to add up all these data values. There's 107 of them, and then divide that whole thing by 107 to get my sample mean, because I assume this is a sample and not an entire population. So what I'm going to do instead, and this is something, on your tests that you're taking in my class anyways, I'm going to give you smaller data sets for the most part. I'm not going to give you ones that have over 100. You might see some with like 30 or 40, and not a whole bunch of those either, because I know that's time consuming. But on your test, you'll be given data sets that are hopefully more manageable, and you might have to type in. It's still tedious, but typing in 30 or 40 numbers is not actually so horrible. 107's getting a little bit ridiculous. All that is to say, what I'm about to do is something you won't be able to do on your test, because on your test, you should be using your calculator. You shouldn't be using other websites or other software or anything like that while you're testing. But I'm going to use a spreadsheet, and I don't have Excel on this computer, Microsoft. So I'm going to use a Google Sheet. And I have the data. I downloaded it from the website, from Kaggle, as a comma-separated value file. And then I saved it to my Google Drive, and then I was able to open it from there in Google Sheets. And then in Google Sheets, or if you have any kind of spreadsheet, it's quite good at doing a lot of the statistical analysis that we're going to be doing in this class. In fact, some people that teach, some institutions will teach this class specifically on spreadsheets. And so all your work is done on spreadsheets. That's not quite the way we do it. We like to use TI calculators or Casios or something there's calculators that can do statistics. And that's kind of been our focus at our institution. Anyways, so the way I'm about to do it may not be the way you will be doing it on your test, especially if you're in my class. But let me go ahead and pull that up on my screen. So here is the same data set, 100, 100, 100. You saw that's how the data set starts out. And so what I did, I actually already did the calculation. I I don't remember if I highlighted it, but I went below this entire data set. So there's 107 data values. And here, what I typed in, and so this will work on spreadsheets. I don't know if you can quite see that, but if you want a spreadsheet to do a calculation, you have to type in equal sign first and then tell it what calculation to do after that. So you do equal, and then you could do 3 plus 5, and it'll show 8 in the cell when you hit enter. So if you put equal there, it'll do whatever math you have after the equal sign. And for a spreadsheet, if you want it to add up a set of numbers that are already in the spreadsheet, you use the sum function. And so SUM is sum. And I don't know if it has to be all caps. Again, this is Google Sheets. It might be different in Microsoft Excel. And then you tell it what cells to sum over. And so this goes from A2. And the reason we start at A2 is because you see the first row is the header. It doesn't have numbers. So our first number is at A2 all the way down to A108, which is this value here. So this function will add up all the numbers from cells A2 all the way through to A108, and then put the result in this column here. So when you add up all of our data values, you get 9,698. So let me go back to this. And so when we add up all of our data values, we get 9,000, and I've already forgot the digits, 9,698. And then we're going to divide that by 107, which I also did on the spreadsheet. So that's what you see right here. So if you look, I took the number from A109. I could have just typed in the number itself, but I said, use the number in this cell. And notice I put equals. It's kind of hard to see there, but it's right on the edge. Equals the number in this cell, A109, which is the sum that we just had, divided by 107. And that gives me 90.6. So I'm going to, and there's more. It's a run-on decimal, but I'm going to round to 1 decimal place, which is what's appropriate for this data anyways. But Math Excel, or sorry, I keep thinking Math Excel because that's what we were using before. We're now using MyStatLab. The directions in the homework should tell you how far to round it. And so it'll tell you round to 1 decimal place. All right. And so that's the mean for this set of data. That's adding up all the data values in the set and then dividing by the total number of data values. And we use this symbol because this is a sample. And so this would be a sample mean, not the population mean. The population that this is representing is the population of all critics everywhere. Or either you could maybe limit it critics in the United States, but I would just say let's the population be, because I don't know if all these data values are limited to just the United States. I would imagine they are including critics review scores from other countries. And so this is, we're studying the population of all critics in the entire world. And this is our sample. I don't know if they collect it in a random way. So again, I don't know the background information for how the data was collected to know if this is truly representative of all critics in the entire world. But that's the idea. We have this sample. We hope it's representative of all critics in the world and what they would rate Animal Crossing. Okay, so that's how you do mean. Median is the number exactly in the middle of a set of data values when it is arranged in numerical order. So this is taking the idea of measure of center quite literally. This is saying the number exactly in the middle of your data set is the measure of center, right? The number exactly in the middle, physically in the middle, is the middle of your data set. That's what the median is. But you have to arrange it in numerical order from lowest to highest or highest to lowest. It really doesn't matter which direction you go, but usually lowest to highest. And then you find the number exactly dead center in the middle. That's going to be your median. And so let's go ahead and do that with this data set. Well, I guess I don't know, I kind of wanted to make this point in just a minute, but we're going to go back to the Animal Crossing critic reviews. Now remember, there's 107, and this is actually going to be important for finding the middle of a set of data. So let me give you a quick example here. Let's go back to this, just so you know why it matters. So let's say we have a data set of just 5 numbers, 3, 7, 8, 9, and 20. let's say. Just making up 5 numbers. What is the middle? And I put them in numerical order. What is the median here? What is the number exactly dead center in the middle of that set? Hopefully you see it's 8. And that is correct. So for this data set, the median would be the number 8. And if you look at it, it is exactly in the middle because how many numbers are to the left? We have 2 numbers to the left. How many numbers are to the right? We have 2. So 8 is exactly in the middle. There's just as many data values to the left as there are to the right. That's what makes 8 the median. That's why it's exactly in the middle. And this is for an odd number of data values, right? Because n here is equal to 5. And that's an odd number. Sorry, I wonder, I don't know if it happens a lot. I'm just now noticing it, but like my desk is kind of shaky and it just shakes my whole setup. So I'm sorry if that's a little bit disorienting for you. I'll try not to bump the desk while I'm writing. What if there was an even number of data values? So let's do this down here. Let's say we have 6 data values instead. So now we have an even number, right? So let's have the same numbers, 3, 7, 8, 9, 20, and 21. I'm just going to make up another number. Now you might say, well, if there's 6 data values, what would be right in the middle? Would be 3, right? Because if you take the number of data values you have and you divide that by 2, that should tell you the data value that's exactly in the middle. So you might say it should be the third one, right? If there's 6 data values, the third one should be the one that's right in the middle. So we go to the third one, which again is 8. This is the third data value. Excuse me, I'm spitting. But that's not actually in the middle, is it? How many data values are to the left? 2. How many are to the right? 3. So 8 actually is not exactly dead center, right? There's less data values to one side than there are to the other side. So it's a little weird because, you think even an even number of data values, there should be some, that should be the one that has the middle. But actually it's the odd number of data values that actually has a number exactly in the middle. Even number of data values, there isn't a number exactly in the middle. So what we do is instead of taking the third data value as our median, because it's not exactly in the middle, we take the third and the next one after it, the fourth one in this case. Now, if you consider this grouping to be your middle, there's 2 to the left of that grouping, and now there's 2 to the right of that grouping. And so 8 and 9 together make up our center, our middle for our data set. And what we're going to do is we're going to take an average or a mean of those 2 numbers. And so I'll take 8 plus 9 and divide it by 2. And that gives me 17 over 2, which gives me 8.5. And so this time our median is going to be, I don't know what I'm doing down here. Our median is going to be 8.5 instead of 8. All right. So finding the median, this is the one complication. If there's an odd number of data values, it's the more straightforward case. And there's one way of doing that. And if there's an even number of data values, it's a little more complicated and has to be managed a different way. And so that's what this screen was about. So let's go ahead and talk about it, right? So if you have an odd number of data values, you find the n plus 1 divided by 2 value in the data set. So you arrange it in numerical order, and then you count. This is the first data value. This is the second one. This is the third one. Keep going until you find the n plus 1 divided by 2 data value in your data set. And that will be the number exactly in the middle of your set of data. So again, if n was equal to 5, like it was here, we take 5 plus 1 divided by 2. That's 6 divided by 2, which is 3. That means we take the third data value in our data set, which is 8, right? So you count. This is the first data value. This is the second data value. This is the third data value. And that will be my median. All right. And so it gets a little confusing. And this is going to continue to be an issue as we go through the rest of the course, that there's numbers on top of numbers on top of numbers, right? We have our original data set. That's one set of numbers, but then we arrange them in order and then we count them. And so 3 becomes the first data value. 7 becomes the second data value. So we're kind of attaching another set of numbers to our original set. And that's going to continue to be the case. Numbers on top of numbers on top of numbers. So you want to make sure you're keeping it straight. It's very meta. If you know what meta means, it's, numbers about numbers, right? That's what we're doing in statistics. All right. So Same issue here. So many data values. Arrange these in numerical order. It would take a while. And I was really hesitant. I'm like, oh, I don't know if I want to take, like maybe I really should get a different data set because I don't want to sit here, even if I don't record it and make you watch me do it. I don't want to sit here for 30 minutes and I know I'll miss some numbers and have to write these in order from lowest to highest. All right, excuse me, I needed to take a drink. Okay. So I'm using the Google Sheet again. And that's what I made this second column for. So I copied all the numbers in the first column, A, over to here. And then another thing you can do in spreadsheets is you can arrange columns in a certain order. Now, here it says you want to do a sort function on this column. Microsoft Excel probably has a more sophisticated version of this because as far as I can see on Google Sheets, like there's just the one option here. And it says from A to Z, which made me think maybe that only does, letters. Maybe it doesn't organize numbers, but I tried it. I just said, let's just see what happens. And it does actually put it in order from lowest to highest for me. So I went to the column up here and I selected sort sheet. Now it doesn't just do the column, it sorts the whole sheet. So notice over here, these numbers also switch to a different order. Now we have 107 data values. So which one do I need to count to? Let's do that calculation real quick. We have 107 data values. It's odd. And so, whoops, I'm skipping ahead. We want to take the number of data values plus 1 and divide by 2, right? If it's odd, we want to use this formula. Number of data values plus 1 divided by 2. So I'm going to get 108 divided by 2, which is going to be 54. Now, here's where people can get confused, especially if that number happens to be similar to the numbers in your data set. Now, 54 doesn't even occur down here, so maybe you won't get confused by this. But some students will say, oh, my median's 54. No, your median is not 54. Your median is the 54th data value in your data set when it's arranged in numerical order. We want the 54th number in our data set. That's going to be our median. So I have to count that. Now, you guys can't see it. Maybe if I minimize this, you could see it. This is kind of handy. So when I sorted this, it put the first value in row 1. It put the second value in row 2. So all I have to do is look for the 54th row, and that will tell me the 54th number in my data set, and that's the one exactly dead center in the middle. There's 53 data values before it, and there's 53 data values after it. Because there's an odd number of data values, the 54th one is the one exactly dead center in the middle. So let's scroll down. So here's 54 right here, and it looks like 90. Now there's multiple 90s, so don't let that bother you, but 90 will be our median in this data set. All right, and so 90 is the 54th data value in the set. Now this is on a separate web page, so maybe after I finish recording the video, I will take a snapshot of the spreadsheet so you can see, because otherwise if you just kind of skip to this point in the video, you're going to be like, how in the world did you get that, right? So there's no work here, no explanation. So I guess it's in the video itself if you watch the whole thing. But anyways, that's the median for this. Now, I wanted to do a similar exercise, but if there were an even number of data values. So we happen to have odd. So what I'm going to do is I'm going to add one more number to this set to make it even. So I'm going to make up something. I'm going to say, I'm an angry reviewer, and I'm going to give this game a 50 because I've never played it and I don't think I want to play it, right? So I'm going to give it a 50. Now I have 108 data values in the set. How do we find the median if there's an even number of data values? We use this other process that we talked about earlier, right? Find the n divided by 2 value in the data set. So we take n divided by 2, find that particular data value in the data set, counting. So arrange it in numerical order and then count to that particular data value in the data set. Take that number and the value immediately following it and average them together. So again, I'm using the word average there. I probably should call it a mean, but you add the two together and divide by 2. And that's how you find the median if there's an even number. Right. So for 108, we're going to divide that by 2, which again gives me 54. That's not my median. That means I want the 54th data value in the set and the one after it. I want the 55th data value as well. And then I'm going to average these two data values together. All right. So let's go back to our spreadsheet. I'm going to undo the sorting that I just did. I'm going to add in, I guess it was at the end. So let me add it in at the end. Okay, oh man. Okay. So it doesn't really matter, I guess, but I'll put 50 right here. All right. Now I'm going to sort this column. So now 50 is first. And I kind of messed up my mean and everything, but I guess we're done with it anyway. So, and I want to count now. Again, we benefit here from the spreadsheet counting for us, because otherwise, without the spreadsheet, if we were doing this on paper, we'd have to count it ourselves. That's 1, that's 2, that's 3, that's 4, and you have to do that carefully so you don't make any mistakes. The spreadsheet counts for us, so the 54th data value is still 90, and the 55th one, the one after it, is still 90. So maybe this was actually still a bad example to use to illustrate how you do median for an even number of data values. But they're both 90, right? The 54th one is 90. The 55th one's also 90. So what do you think happens when you average these two together? The average is still going to be 90. So it ends up being the same as the odd numbered case. But generally, you'll get a different answer, especially if there's some more variability in the data set. We had a big clump of 90s, a big clump of 100s, a big clump of 80s. And so that can kind of, mask what really goes on behind the scenes, right? So you want to follow this process. Don't just hope that, it'll be the same whether it's even or odd. Normally, that's not the case. Normally, if there's an even number of data values, the result comes out a little bit different than if there's an odd number of data values. And, normally it won't just be the same number, right? So the 54th data value is 90. That usually doesn't end up being your final answer, because usually the 55th one will be a different number. So if this had been 91, then our answer here would have been 90.5. So usually these two numbers are different, but not always. Sometimes they could be the same. So anyways, hopefully median makes sense to you, and I'm probably just over explaining it. So let's move on to the last two topics, which are much easier. So we should be done here pretty quickly. The mode is the data value that occurs most frequently in a set of data. So if you think about it in a way, this could reflect the center of our set of data, because the mode is sort of like where the highest concentration of data occurs. What number is occurring the most frequently? Because there's a big clump there, and that really kind of in some way represents the center or the middle of that set of data. So mode is the number that occurs most frequently. It is possible for a data set to have no mode whatsoever. So if every data value occurs an equal number of times, there's no mode. Normally that would be the case where each data value just occurs once. Again, I mentioned earlier, I don't know if I cut it out when I edited the video. I haven't been editing. I've just been like, I'm just going to leave it. Probably just leave this one too. But I'm not a statistician by training. I'm knowledgeable enough that you're going to do fine in this class. You'll learn what you need to learn in this class. To me, I wouldn't think, and this is a fringe case, it probably hardly ever comes up, but I imagine, in math, you have to think about these kind of fringe cases to look for possible weaknesses in your definitions and the way you do things. But I think about, what if I had a data set that each value occurred twice? I would argue that that data set has no mode either. If every data value occurs the same number of times, even if it's twice each time, if they're all occurring twice, there's not one that stands out from the others. So I would argue that data set has no mode. But I haven't really researched it, and I'm not really sure what the consensus is in the statistics community, if that's how they would conclude that as well. So, but I doubt that would come up as any situation that you'll encounter. So if every data value occurs once or an equal number of times, that data set has no mode at all. It is possible for a data set to have two modes. And if it does, it's called bimodal. And so you have two data values that occur with the same highest frequency. This data value occurs 5 times, and this other data value also occurs 5 times. And that's the highest occurrence of any data values. And since there's a tie, they both count as the mode. So you have two modes. And you can even have more than two. And in that case, it's called multimodal. So you might even have three that each occur 5 times. And if that's the highest number, all 3 of those is the mode. All right. So what about this data set? I actually have not done this, but my inkling, because, in chapter 2, we did that stem and leaf plot, and there was a ton of 90s. So let's count the number of 90s in this data set. And I don't think anything else is going to come close to that, but let's just check, right? There is a lot of 100s too, but I'm pretty sure there was more 90s. So how many 90s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 so far, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. I think we can look and see nothing else is coming close to that, right? There's definitely not 37 100. There's a bunch. I think there's like 10 or 14 100s, but it's not going to be 30. And I'm pretty sure the 80s don't come close to that either. So I think it's fairly settled that the mode here, there's just one mode, and it's going to be 90. Right? 90 occurs a ton of times in this set. So if you had to bet, so if we were going to get one more critic review score, and you had to bet what that score might be from that critic, this would probably be your best bet, because 90 by far occurs the most often. So if you think of it, like if we were going to pick a number out of this set at random, most likely we're going to pick 90. It's like a third of the data values. There's like a 1 in 3 chance that if we pick a critic review score at random, it's going to be 90, right? It occurs so frequently. Plus, it's also the median, right? 90 is the median, whether there's an even or odd number. 90 is like right smack dab in the middle. And for the average, for the mean, going back to that, 90.6, right in that same neighborhood. So all 3 of these measures of center really seem to be converging on 90, right? It seems like that's really the center of the data, almost whatever way you want to cut it, whatever way you want to look at it. 90 is right there in the middle, except for this last one, which is also the worst one that we're going to do. The mid-range, the most useless one, is the number midway between the lowest value, which is called the minimum, and the highest value, which is called the maximum in a data set. And remember, we talked about this before. If you want to find, I think we did, maybe that was in a different class. I think I'm thinking of college algebra now. But if you want to find a number exactly, no, we talked about this. We talked about this in chapter 2 because we had to do this for class boundaries, class midpoints. The number exactly halfway in between can be found by adding the 2 numbers together and dividing by 2. And so that's how you find the mid-range. You take the minimum data value in your data set plus the maximum data value and then divide that by 2. And that tells you the number exactly halfway in between the minimum and the maximum. So let's go ahead and find the mid-range for this Animal Crossing. This is also the easiest, it's the most useless one, but it's the easiest one to do as well. The minimum data value in our data set is 70. That's the lowest one. The maximum is 100. So what's halfway in between? We take 70 plus 100 divided by 2. So we get 170 divided by 2, which is going to be 65. Right? No, that can't be right. Can't be that low. It's going to be 85. I don't know why I thought 60. 85. Right. I was thinking 16, and I think I got the 6 from that. But think about, and this is a good thing to do. If you come up with an answer, mid-range has to be between 70 and 100, right? It has to be, we're talking about measures of center. It needs to be somewhere between the lowest and the highest value. So if I miscalculate and I get 65, that should stand out to me like, wait a minute, the lowest number 70, how could it be 65 for the mid-range? Like that just wouldn't make sense, right? So it's good to have a sense of what kind of answer you should be expecting here. And 65 would not be something you would expect, right? So 85, which is pretty close to 90, but not quite there. But like I said, I wouldn't read too much into that. Round off rule, we kind of used this when we did the mean. Carry one more decimal place than is present in the original data set. You might say, why not? What's the harm in just carrying more decimal places? The harm of that, So if we go back to our, let's see if I can undo this again. Okay. We go back to our average here, and I say the average is 90.635514, and that's what I tell somebody the average is for the critic scores. They're going to say, wow, that's really a precise calculation. I hope I'm using the word precise correctly there. I get a little more self-conscious since I'm recording it and I'm posting it to YouTube and other people are going to watch it. There's going to be some statistician that comes along and says, wait, that's not what precise means. There's accuracy and there's precision. Those sound similar, but they're different. And I might be using the word incorrectly. But anyways, if you use a lot of decimal places, you're misleading people into thinking that your measurements that gave you that average were also that accurate, that they were also measured to that many decimal places, right? So we don't want to mislead people. So this is why we want to use this round off rule. Don't carry more decimal places than what you have in the original data. Just go one more than what's present in the original data. If you go any more than that, you're misleading people into thinking the original data set has more decimal places, is more accurate, more precise, more accurate than what it really is. A good example of this would be like if we're measuring heights of people. I'm 5'10", somebody else is 6'2", somebody else, and we average all those heights, and we find that the average height is 5'11" or something like that, right? But if I said the average height is 5 foot, 5.9728, you're going to think, wow, you measured those heights pretty accurately. You went to a lot of decimal places to measure those heights. No, we didn't. We did 5'10", 6'2", right? We were rounding our heights. But then when I present the average with a lot of decimal places, people might read into that and think I measured the heights to a lot of decimal places to get a precise calculation for the average when that's not the case, right? So that's what we want to be careful of. Okay, so that's what the round off rule is about. And the last topic in this video, the mean of a frequency distribution. This one's kind of challenging. Hold on one second. Because you don't have the data set. So let's look at this frequency distribution here. This was from chapter 2. Now we have the Animal Crossing data in our video, but if I didn't provide you the Animal Crossing data and I said, here's information about your data set, and it's a frequency distribution, you do not have the original data values in that data set. You do not know that from 71 to 80, you don't know what those numbers were. All you know is that you have 11 data values somewhere between 71 and 80 inclusive. We know from our data set that, in fact, this is kind of interesting, all 11 of those data values were exactly 80. But you wouldn't know that from the frequency distribution. You don't know, there could be one that's 71, there could be one that's 72, one that's 73. We don't know what those 11 data values actually are. We just know that they're somewhere between 71 and 80. Same thing for the next one. There's 59 data values between 81 and 90, but I don't know exactly what those data values are. So if you ask me to find the mean of a frequency distribution, that's a difficult thing to do because we don't have the data values. So all we can do is estimate. And that's what we're doing here. So I'm going to guess. So I don't know what these 11 data values are. So let me guess what they might be. What would the best guess be for the data value here? Now, if you say, well, the best guess would be 80. Well, that would actually be a great guess because we know that's exactly what they were. But you don't know that. And what if a data value, what if we guessed that these were all equal to 80, but they were all 71 instead? We would be really far off. We'd be 9 away from what the data value actually was supposed to be. And so that would really throw our estimate off for the mean. If you go the other way, so again, so 80, maybe that was a bad example. What if you decided to say, let's just say they're all 71. We have 11 data values here. Let's just say each one of them is equal to 71, and that's what I'll use to calculate the mean. But they're all 80. So you're way off the mark. The safest choice to make here for estimating the data values in this class is to use the midpoint. That's exactly in the middle between these two numbers. And that way it minimizes the potential error, right? And so the midpoints here were 65.5, 75.5, 85.5, and 95.5. Those numbers are the numbers exactly in the middle of each of these classes. And that is the best guess for what the data values actually were, so that you minimize how bad of an error you might make in estimating them. Because again, if you go to the extreme, if you go with one of the lower class limits or upper class limits, you're taking a big risk that the data values are actually on the complete opposite end, which makes your estimate worse. The safest estimate, the safest way to get the best estimate is to use the midpoint. And I chose this data set on purpose because we actually know what the mean is supposed to be. It's 90.6. And I'm really curious, honestly, when we estimate it from the frequency distribution, how close it is. Right? It's not going to be exactly right. I don't know if we get lucky, maybe it is, but I wouldn't expect it to be exactly 90.6, but I'm hoping it's somewhere in the neighborhood. So we can see that it's a valid way of estimating it, even though we don't know the actual data values in the data set. So what we're going to do is we're going to say, okay, there's one data value in this class. We're going to say, let's assume it's 65.5. That's the safest guess for what that data value happens to be. There's 11 data values in this class, so we're going to say all 11 of those data values is 75.5. So we're going to have 75.5 added to this list 11 times. Right. And then for this class, there's 59 data values. We're going to assume they're all 85.5. So I have 85.5, 85.5, ... 59 times. And then for the last class, we have 36 data values. We're going to assume all 36 of them are 95.5. 36 times. All right. And that's what we're going to find the mean of. So we have to add up all these data values. Now, there's 107 again, right? Because that's how many data values were in the data set. We're going to have to add up all, there's one right here, I guess. So we're going to have to add up all 107 of these numbers, right? Because we have this number here 59 times, this number here 36 times. But because we're repeating the same number over and over and over, instead of having to add it individually each separate time, there's a shortcut. That's what multiplication is for, right? If you have 2 times 5, that's the same thing as having 2 plus 2 plus 2 5 times. And that's exactly what's going on here. We're going to have 85.5 plus 85.5 plus 85.5 59 times. The shortcut for adding 85.5 59 times is just to take 85.5 times 59. And so to find our mean, we're going to take 65.5. That was a horribly drawn 5. 65.5 plus 75.5 11 times. So instead of adding it 11 different times, I just multiply it by 11. It does the same thing. Plus 85.5 59 times. So we'll multiply it by 59. And I was hoping I would have enough room here, but I'm almost out. Maybe it'll fit. 36 times 95.5. All right. Hopefully I said it. I know it's hard to read, but I said it. So hopefully you know what that is. And then we'll divide by the total number of data values, which again is 107. Right. And that's going to give us our estimate for the mean based on the frequency distribution. So I'm going to pause the recording because again, I guess I have my phone. I guess it wouldn't be too bad to do on my phone. Just not used to it. Where is oh, that's the clock. Okay. I'm giving my age away by how inept I am at using my phone. Okay. So we will have 65.5 plus, I don't know how I want to do this. Let's do it one at a time. 11 times 75.5. Let's start with that. That's 896. Okay, so we're going to have 65.5, which is just going to be 65.5. 896 from the 11 times 75.5. We'll have 59 times 85.5, which is 5,044.5. Okay. Trying to think, does that make sense? That's one. I don't know if that makes sense. Hold on. Let's check that again. All right, 11 times 75.5. I had a feeling that wasn't right. So what made me pause there is these are both odd numbers. And when I multiply them to that 0.5, like this one came out as a decimal and this one came out as a whole number. I'm like, that doesn't seem Like, because they're both odd numbers, I would think they would have the same kind of answer. If one's a decimal, the other one's a decimal. So I don't know what I typed into my phone the first time, but now I'm getting 8. Oh, probably because I added the 65.5. That must have got added in. So this should be 830.5. I apologize for that. Plus, this will be 36. So let me clear that out. 36 times 95.5, which is going to be 3,438. Okay. And then we're going to add those numbers up and divide by 107. So I'm feeling really bad about this. Let me rewrite that again. 36 times 95.5. I just want to make sure you guys can see what I'm doing there. And this one's kind of bad too. This was 59. Okay. And we get these results. Cross out the 896. So now I want to add these four numbers together. So I'll go ahead and do that. 65.5 plus 830.5 plus 5044.5 plus 3438. And I get 9,378.5. And I'm going to divide that by 107. And this is going to give me my mean, but it's an approximation. It's not exact because we didn't use the exact data values from the data set. And you see we are a little off the mark. It's 87.6 when you go to one decimal place. So that would be our estimate for the mean of this data set using the frequency distribution. And it's pretty close. I mean, I'm pretty happy with it. You might feel like, oh, that's really far off, but it's not actually that bad. It's pretty close to what the actual mean was. And that's what should happen. Okay. Sorry, this video is getting a little bit lengthy. I do have a couple more examples here that I wanted to go over. These are from the homework. So what I would like you guys to do is pause the video, find the mean and the median. Let's not do both of these. I was going to, because there's that interpretation. Does there appear to be a difference? And I thought maybe there was something to be said, but these are fairly like obvious comparisons. You know, I thought there would be some interpretation involved, but it's just really like, are they close to the same? Is one lower than the other? Is one bigger than the other? So I think once you have the answers, it'll be obvious which one of these is correct. So let's just do the female group. So I'm just going to do, or maybe we could just do it like this. You could do the male mean and median. I could do the female mean and median, and then you could compare and see what the answer should be for the next screen. But I'm not going to do the male set. I'm just going to do the female set. All right, so I'm going to pause the video. You should do the same. Calculate the mean and the median given these numbers. And this is more like what you'll see on the homework. You're not going to have 107 data values most of the time. It's going to be more like this. You know, there's like 12 here or something like that. So find the mean and the median, and then resume the video to see if you came up with the right answer. Okay, so here is the work for this particular problem, looking at the data set for the female pulse rates. For the mean, I did the work down here. So we added up all the data values. I didn't write out each particular data value, but just to make sure it was clear how I got to the result. 69 plus 75 plus 90, so on and so forth until you get to 76 plus 71. Add all those up. I got 1,199, and then divide by the total number of data values. Before I said pause, I said it looks like there's about 12. I hope you didn't use that in your calculation. I hope you actually confirmed that the number of data values was actually in fact 15 and not 12. And so you find there's 15 data values. Divide those. You should have got 79.9 for the mean for the female data set. The male data set might be different than that. For the median, you have to take these data values and write them in numerical order. I know it's kind of a hassle and a little bit tedious, but that's what I did up here. I actually had to erase a couple times because, well, in fact, I started with 69, and then I realized when I got here, I was like, oh wait, there's one before that, so I had to write 64 first, and then it's like 76 at one point. I think I missed another one over here. So, but eventually get them all in the right order. There's 15, which is odd. It's an odd number of data values. And so the process for finding the median is to add 1 and then divide by 2. So we get 16 divided by 2, which gives me 8. Now 8 is not the median. The 8th data value in the set is the median. And so I numbered them here so that it'd be easy for me to find. 78 is the 8th data value in the set. So that's going to be our median. The problem doesn't ask for this, but I just thought it'd be a good exercise. So just real quickly, what do you think the mode is? This looks like mole, but I'm asking for the mode. Which data value occurs the most frequently? And there's only one that occurs with any repetition whatsoever, and it's 90, right? And it occurs 3 times. So there's only one mode in this data set. It is also 90. And then for the mid-range, you take the minimum value in your data set, which is 64, plus the maximum data value in your data set. So for the mid-range, we're going to take 64 plus 95, divide that by 2. And I'm not going to write out the details, but I did this in my calculator, and I got 79.5. So that's what you should get for the mid-range. All right. So not that it asked for that, but just to kind of, review all the stuff we talked about in the video. I said we're going to skip that one, and I apologize that this is way off the mark here for some reason. Okay. So, and this is an example of finding the mean from a frequency distribution. So with the Animal Crossing, you might have felt a little frustrated, like, why are you making me do this? We have the data set. Why would we want to estimate it from the frequency distribution? But anytime you're developing a process, you want to make sure you have some way of confirming that it's reliable. So I like the idea of using the frequency distribution from the Animal Crossing data so that we could check with the actual result just to see that it does indeed estimate it. It gets close. Here, we don't have that luxury. We're given the frequency distribution, and we don't have the original data set. Now, they actually do tell us here, compare it to the actual mean of 52.3. So they don't tell you the original data set, but they do tell you the actual mean is 52.3. How does that compare to the mean that you're finding from the frequency distribution using the process that you use to estimate? And you should find that it's close. So whatever you end up getting, the answer you want to choose there should be something like it's close to the actual mean. The frequency distribution estimated mean is close to the actual mean of the sample. So pause the video again, because we already did this one time. I want you guys to try it. If you're watching the video, math is about practice. So we've done it once already. Pause the video so you have a chance to practice it. And then I'm going to pause my recording. I'll work out the answer, and then you could check to see if you came up with the right result. And, if you're looking at this and like, I'm not even sure where to start, go back and look at the example we just did a few moments ago and review it, and then give it a try. Because, when you sit down on a test, you want to be able to look at this problem and say, okay, I know exactly what I need to do without any, leads. So you need to know what to do with it. So anyways, pausing it, and I'll resume it here in just a minute. Okay, so that didn't actually take as long as I thought it would. I did realize I skipped a screen back here for finding the mean of a frequency distribution. There's actually a way of writing that in formula form using the sigma symbols that we talked about earlier. So remember, this means the sum of, and what you're going to sum up here, for each class, you take the frequency times its midpoint, right? So the X represents the class midpoint. So just like we did in this example here, right? We took, it's right here, right? We took, this is the frequency right here, times the class midpoint. This was also the frequency times the class midpoint. So for every class, you're taking its frequency times its class midpoint, and then you're adding them all up. You're summing that, right? So you're summing the frequencies times the midpoints. And then the denominator also has a sum. It's the sum of the frequencies, which is what n is equal to, right? We talked about this back in chapter 2. If you add up all the frequencies, it should add up to the total number of data values in the data set. So the sum of the frequencies is your value for n, which is what you want to divide by when you're finding a mean. And so we didn't have to do that here because we already knew it was 107 because we had been working with this data set for a while now. But if I didn't know that, I would have to add these up. It adds up to 107. Sorry about that. Adds up to 107. And so this is the sum of the frequencies, which is what n is equal to. And that's what we end up dividing by. So I'm sorry I did leave out that little bit of detail, which might have made doing this problem a little more difficult. But hopefully we've talked about these concepts. So hopefully you're able to kind of piece it together. And so while the directions don't say find the class midpoints for these classes, you have to know that's what you need to do first. So you want to find the class midpoint here, which I was able to do by just eyeballing it, right? We have 40 and then 44 as the upper and lower class limits. What number is exactly halfway in between 40 and 44? It's, I don't know, to me, obviously 42. It may not be that obvious to other people. If it was 45 to 49, I feel like that one's not so obvious, but I think I probably could have figured it out without having to write out a calculation. But you want the number exactly in the middle. It's going to be 42. And then the class width, remember, here is 5. So the next midpoint would be 5 up, which is 47, then 5 up again, which is 52. So it kind of cycles back between 2 and 7, 2 and 7. And then, so those are the class midpoints. So I took each class midpoint times its frequency. And that's how I got this first line right here. 1 times 42 from the first class, 6 times 47 from the second class. Because remember what we're doing, we don't know what the data values actually were. We just know there's 6 data values somewhere between 45 and 49. Our safest estimate for what those data values might have been is to use 47, which is exactly in the middle. And that hopefully minimizes the distance that we are from the actual data values. Right. We have 11 data values between 50 and 54. I'm just going to assume all 11 of them are 52, again, because that's right in the middle, and that minimizes our risk of error of being too far off from the actual data values one way or the other, and so on and so forth. And so that's how I got this line right here. And then so I did these individually in my calculator because I don't know if the iPhone would let me type in all of it at once. It probably does, but I just did one at a time, got these numbers, added them up. Right, so I added up these results and I got 1,310, and then I divided by 25. So you have to divide by the total number of data values, which you can get by adding up the frequencies from the frequency distribution. So if you add up all the frequencies, you get 25. That's how many data values there are here altogether. So we divide by 25. We get 52.4, which is really, really close to the actual mean. So I think there's just no debate this time. It's just right exactly about where it should be. So this is actually a very good way of estimating the sample mean, even though we are actually missing the original data set. And we're just having to use these estimates, these classes to kind of estimate what the data set might have looked like. Okay. So that is the end of the video for section 3.1. I will see you in the video for section 3.2.